Hi, I'm Khalil Anderson. I'm just here to explain my machine learning project. And what I worked with was doing spatial analysis. And so what I wanted to analyze was the spatial effect of education, or do some spatial regression over education using some economic and county census demographic data as determinants to see if we can actually correlate these factors. And we want to also take in the spatial dependencies that are inherent in the space because of the first law of geography, which says things near each other are more related, which we will see is actually true in this case, in that um, like neighboring counties are spatially related to other neighboring counties' college education values. So here we dive in. So look, the reason for this was that there's a major decrease in the people who out earn and out learn their parents. Before it was 90% out earn, now it's 50%, and before it was 70% out learn, now it's 45%. The previous numbers were in the 1940s, and this was currently in 2018. This is all from a Forbes article in 2018. So, what I did was I took advantage of census data and economic data provided by the government. Most of it is census data, because there's actually a lot of data on the website, and I collected. I um, kind of did some work in Excel to put it all together, put it in the right format, put it in the way that I wanted. And I had to go into QGIS to actually spatially join the data with actual county spatial characteristics. And then I got rid of in that like county spatial data, I had to get rid of the empty information and actually get that final shapefile along with this final spatial data. Um, and so that's the final spatial data is what we use. And we also need the shapefile because we need to get the spatial weights, which is what's the important part for the spatial model, is that these spatial weights are going to allow us to calculate how much of an effect these dependent neighboring counties' college education rates are on the other in our model, which is going to be they're going to see there is a difference. It may be small, but and it may be small, but in some higher correlated domains, it's going to be much larger. So it might be something to always keep in mind and it's something to key to actually deal with in terms of dealing with in your model. So here we go, we dive in. So we import some models, and PySal is the key model that actually calculates most of the spatial information. And so I'd taken the data and I'd taken the y-index, which is what we're calculating, the correlation, they're doing regression to calculate, and the x-index are obviously our features. And so then we get those all into an array and we split them into the y and the x's and we calculate the spatial weights using the shapefile that we created. And like I said, the shapefile is the projection of all the counties, or it's the file that describes how the counties are shaped. And so from that, we can actually calculate the spatial weights into what we call the Queen's spatial weighting, which says that any counties that share a vertex and edge are neighbors. Meanwhile, the other weighting is Rook, which is just if they share a vertex. Um, and that's a full vertex. So it yeah, it's not as strong. Queen is just any neighboring, and it's the more natural um, weighting. And so then we also need to calculate the lag for our Durbin model, and so we are calculating and comparing multiple models, OLS, the spatial error, the spatial lag, and the spatial Durbin. As you can see with the Durbin, the added is the W, the spatial weighting times X theta. And so this is actually what we're calculating in a spatial lag calculation with our spatial weighting. And we stack that with our just regular X values into a Durbin X. And this is what we're going to run through the lag model, because the Durbin is just the lag model with the added weighting to the model to learn in the model. Um, and so we also calculate the spatial autocorrelation, which is the Moran's I. And so what this says is how spatially autocorrelated the variable is to its neighbor's own variable of itself. And so what that says is that for any 10% increase in college in college attainment in a neighboring county, it has a 12%. Any 10% increase is a 12% increase in another county. Is 12% of that increase in another county. Um, so we run those through each of those models, and we do show the difference between the OLS model and the Durbin model's coefficients just for comparison. But the biggest comparison we're going to see is there is an increase between the OLS model and the Durbin model R squared. So you do see it actually does fit it better when we actually take into account that information. Um, and so you can see also it improves the lag model, doesn't improve as much, but it still improves the combo, doesn't improve. The error model actually doesn't improve. But it's interesting that the lag and error combine, which makes sense. Taking them both into account is going to just improve even more, but it's interesting that the error itself did decrease it. But this is just kind of exploration of spatial analysis and spatial data. And this is what I did for my machine learning project. I hope you guys liked it. All right, bye.